Okay, ladies, so here is our first experience of a flipped classroom in biology where you will cover notes using a video rather than in class. I really like this option for when I can't be at school or for when we have online school, or as you'll see in the coming units, we might do some notes this way to free up more class time for doing labs and other activities. So we're going to run through the first couple pieces of these Chapter 2 notes this way, and then we'll do the rest of them in class together later on. Here are your essential questions. Basically, what we're most interested in is how does chemistry or why does chemistry matter in biology? So this whole section is chemistry, and some of you might have had some of this as sixth graders, or as seventh graders, or as eighth graders, or maybe barely at all. But there really are some components of chemistry that are essential to biology, and that's what we want to look at. And so we're going to take some time to look at what is matter, what is water, what are the different types of biomolecules or carbon compounds, and then maybe most importantly, what are enzymes. So, as I was just saying, we're really only going to focus on the parts of chemistry that have to do with biology. But honestly, there would not be biology without chemistry. Um, Basically, there's no life without chemical reactions. And so, just as a couple of basic examples, when we eat, right? When we eat a food, we have to break that down into nutrients that our body can then absorb and that our cells can use. If we don't break the food down, our body can't do much with it. So that would be an example of some chemical reactions that start in your stomach, or actually they start in your mouth with your saliva, and then proceed as you digest your food. There's also a lot of chemistry that goes along with how we breathe. Right? When you inhale oxygen, we have to basically dissolve that into your bloodstream, into a liquid, move it to your cells, and then release it from that bloodstream again. This is going to involve several chemical reactions, kind of on both ends. So without chemistry, you couldn't breathe either. So what it really comes down to is chemical reactions. We have tons and tons of reactions that you need for your body to work correctly. All right, now here's Bob the Builder. Many of the characteristics of living things that we have covered in our first chapter depend on chemistry in order for them to work. Basically, to do homeostasis, you need chemical reactions. To respond to the environment, so to even sense that something is flying at your face, so then you dodge it by ducking out of the way, you need chemical reactions. In order to grow and develop, you need chemical reactions. And probably the biggest one of all is in order to obtain and use material and energy, in order to have a metabolism, you need chemical reactions. So, just as Bob the Builder here, or an architect, has to understand their building materials before they begin to create a building, we have to understand the chemical building blocks that the body is made of in order to understand the body. If you want to build something out of bricks, you have to understand how bricks work, how much weight they can bear, and those kind of concepts. And so, if we're going to understand how your body works, we need to understand what it's made of. Okay, so the basic unit of matter is called an atom. And I'm pretty confident you've heard this before, but again, it might have been 2 years ago, 3 years ago, last year, so we'll make sure that we review all of this. Atom, A-T-O-M, comes from the Greek word atomos, which means unable to be cut. And this Greek philosopher Democritus first described an atom and believed that it was the smallest thing possible. So you couldn't cut it any smaller, and you can see a cool illustration of an atom right here. Now, since that time, we've learned that an atom, is made of smaller things. And basically, there are three subatomic particles. The first one is called a proton, and protons are found in the nucleus, the central area of the atom, and they have a positive charge. Now, then you also have neutrons in that atomic nucleus, and they do not have a charge at all. So we say they are neutral, hence the name neutron. And then we have electrons. And electrons are unique in that they orbit the nucleus. So they kind of fly around the outside of this nucleus. And electrons carry a negative charge. So you got an atomic nucleus, central ball of protons and neutrons, and this electron cloud that orbits it. When we look at an atom, it will usually have the same number of protons and electrons. Hence, that atom itself is neutral. So for example, if you have 3 positive protons and 3 negative electrons, they'll cancel each other out and your charge will be 0. Now another vocab term here is the term element. An element is a pure substance that consists only of one type of atom. So there are over 100 elements that we see in nature. Really only 26 of those appear in living things, and only 6 to 10 or so of those are really all that common in living things. So as you might guess, we're going to focus here, and there are going to be a ton of elements that you don't need to really know about. Now elements we always represent with a 1 or 2 letter symbol. You're hopefully familiar with this a little bit from science in the past, and I will expect you to know some of these symbols. So a couple of examples here would be carbon is a capital C, oxygen is a capital O, and then sodium is Na, which comes from a Greek or Latin version of the word sodium. So here are the elements that I really want you to be familiar with, and so that means these are the elements that I would expect you to know the symbols for. Now the human body is primarily made of these 6 elements, and the way you can remember those 6 is SCHNAPS, because these are the abbreviations or symbols for these 6 elements. Your body is primarily made of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, and all of these are abbreviated by their first letter. Now you also need some smaller amounts or trace amounts of a lot of other elements, but I'd like you to be familiar with these here on the screen now. So sodium, we saw on the last slide, is Na. Potassium, anybody know it? It's K. Alright, magnesium is Mg. Calcium Ca. Iron Fe. Manganese is Mn. Chlorine is Cl. Iodine is just I. Cobalt is Co. Zinc is Zn. And fluorine is just F. So these on this slide I would expect you to be familiar with and comfortable with. If it's not on this slide, it's not one that I expect you to know the symbol of or know that much about. Now the nice thing is, we have a periodic table that organizes all of these elements for you, as seen here. Now the periodic table is meant to be a tool. So maybe in other classes, even here at Mercy, you will be expected to kind of memorize parts of the periodic table, but that is not the way it's going to work in this class. If I expect you to know something from the periodic table, you will have a periodic table to look that up on. So if you notice in the Unit 2 folder of this unit, you will find a periodic table there as a PDF file. You can always pull that one up on your iPad and use that if you're working on homework or working on a lab in class or something. But also, when it comes time to take a test over this stuff, if you will need a periodic table, I will give you a copy of the periodic table to use. Now, the most important thing then is that you have to know how to use that periodic table. So, we look at a few different things. Inside the periodic table, you will see that we've got all the different elements. So let's take a look at this carbon box. Alright, 6C. So we zoomed it in here. Now, the number that's usually larger at the top of one of these boxes is the atomic number of that given element. And the atomic number is the number of protons that we find in an atom of that element, and that's what defines that element. So if something has 6 protons, it is carbon. Now, the way the periodic table is organized is by those atomic numbers. So you'll notice that those atomic numbers keep coming up here as we just move along. each row from left to right. Now also in this box you're going to see the symbol of the element, and you're going to see the mass of that element. Now let's do a little seek and find. So you've got a periodic table in the Unit 2 folder that you can open up. Take a moment, pause this video, and fill in this table in your notes. Then we'll go over the answers and make sure you have them correct. So go ahead and pause that now. Okay, hopefully you really paused your video. Let's go ahead and fill these in real quick. So carbon, abbreviation should be C. You'd find that this is in the second row of the table, going from left to right, and that it is found in the 14th column. And that has the atomic number of 6. Now our second one here, if it's abbreviated O, it must be oxygen. Oxygen is going to be found in the second row as well, but in column 16, and it has the atomic number of 8. Third one here, atomic number 7 tells you that you're looking for nitrogen, or N. It's also going to be in our second row, and it's going to be in our 15th column. Hydrogen is really easy. Hydrogen is abbreviated with an H. It is in the first row and the first column because it's the very first element on the upper left, and it has an atomic number of 1. Now if we look in the third row in the 16th column, you will find sulfur, which is abbreviated with an S. This has an atomic number of 16. And then the element that's abbreviated with a P is phosphorus. That's going to be found in row 3, column 15, with an atomic number of 15. So make sure you find me later and ask me if this was confusing to you at all, and we can look at that periodic table some more together. Now, atoms of a particular element can have a varying number of neutrons in their nucleus. Again, the proton number will be the same, because the proton number is what makes it that given element, but the neutron number can change. An isotope is an atom of the same element with a different number of neutrons. Now, really important thing that you're going to have to be able to do later is to calculate the mass number. Now, the mass number is the sum of protons and neutrons. So in other words, the mass number equals the number of protons plus the number of neutrons. And this is how we would identify different isotopes, is by their mass number. Now these would be 3 different isotopes of carbon. Again, if it's carbon, it has the same number of protons, so each of these would have 6 protons. But their masses, here 12, 13, and 14, differ because they have different numbers of neutrons. So for instance, carbon 12 has 6 protons and 6 neutrons. Carbon 13 has 6 protons but 7 neutrons. And carbon 14 has 6 protons, again, but 8 neutrons. Now some isotopes are radioactive, which means that their atomic nuclei are unstable and they break down at a constant rate over time. This is the main reason that we care about isotopes in biology. So radioactivity, you've probably heard before, this is dangerous. I mean, you don't want to be radioactive and you don't want to come into contact with lots of radiation. But radioactive isotopes can be used for a lot of stuff in biology. One that you've maybe heard of before is radiocarbon dating or carbon-14 dating. Again, we know how long it takes a radioactive nucleus of a particular element to break down. So if we look for carbon-14 in some ancient fossils, some ancient rocks, we can kind of see how much of that is left, and we can estimate how long it's been around because we know how long it takes that stuff to break down. A couple other isotopes that we see in medical science are strontium-89, boron-10, and rhenium-186. These are not the only 3, but these are 3 of the main radioactive elements that we use in radiation therapy for cancer patients. We'll talk about that more later this year, but you maybe have heard of people, maybe even a family member, who's had radiation before when they have cancer, and they're using radioactive elements to do that. Now, we can also label things in research science using radioactive isotopes. So this is a little deeper than I'm worried about you guys understanding, but basically we can stick a radioactive element into something or onto something, and it might allow us to see that something better in our lab. We'll kind of talk about examples of that later this year also. Now, most of the elements are not found alone, but rather they are found in combination with other elements in compounds. And there's a couple different types of compounds that we will see. Now, the components of a compound are always expressed in the chemical formula. And the chemical formula tells us what elements and how much of each we're going to find in a particular compound. So for instance, water. I'm guessing you know water's chemical formula. I hope you do at least. It's H2O. So what that tells us is we have 2 hydrogen atoms for every 1 oxygen atom, and that gives us water. Now, NaCl is another chemical formula. You might know that this is sodium chloride. You might also know that sodium chloride is table salt, right, that you would maybe put on some food or something. Now, what we learned from this is that sodium chloride is made up of sodium and chlorine, and they're found in a 1-to-1 ratio. And so there's 1 sodium for every 1 chlorine in this compound. Now, the different types of compounds are determined by the type of bond that holds them together. So there's lots of types of chemical bonds out there. We're really only worried about 2 types, 2 major types, and we'll review these together next time in class. The first type is called an ionic bond. An ionic bond is where 1 or more electrons actually gets transferred from one atom to another. Now, this forms an extremely strong bond between the atoms, because this means that you take an electron from one atom and you give it to the other atom. Now, remember that atoms, as we saw earlier, are usually neutral. They have the same number of protons and electrons, and so they stay neutral. There's no charge. But an atom can become an ion if it gives up or gains an electron. Then it will have more electrons than protons, or fewer electrons than protons, and it will have a positive or negative charge. So, if an atom loses an electron, gives away a negative, it becomes positively charged. If an atom gains electrons or gains negatives, it becomes more negative, so it becomes negatively charged. Now, the classic example of this in nature is sodium chloride. Right? Sodium chloride forms an ionic bond, which means that one of these atoms actually gives an electron to the other atom. In this case, it is sodium that gives an electron to chlorine. So you can see here in this picture, right, we start out with sodium right here, and then chlorine. The sodium will actually give an electron to chlorine. Now, this makes that sodium and that chlorine want to stick together really tightly in nature. But what we've really created when we did this is a sodium ion with 1 less electron and a chloride ion with 1 more electron. So check it out. If we take an electron away from sodium, we now have 11 protons and 10 electrons. 11 positives and only 10 negatives, so now we have a positive 1 charge. But if we add an electron over here to chlorine, we've added a negative, so it's going to become a negative 1 charge. The other type of bond that we see in nature is called a covalent bond. And a covalent bond occurs when atoms share electrons. So they don't completely give an electron to the other. That's what an ionic bond is. But they just share electrons. So the electrons, which were already orbiting the nucleus and flying around, they will actually travel around both atoms. So if we look at this water molecule up here, right, a water molecule is a sharing of electrons between hydrogen and oxygen. So if we follow one of these electrons, it'll follow these kind of light blue paths they show. It might go around the hydrogen and then the oxygen and the other hydrogen and the other hydrogen and the oxygen, and it just keeps orbiting like that, and it spends roughly equal time with both the atoms. So it's not just given up, it's shared. Now, covalent bonds can involve multiple electrons. So you can have single covalent bonds, double covalent bonds, or even triple covalent bonds. But when it comes down to vocab again, if a compound is formed by a covalent bond, we call it a molecule, like this water up here. If a compound is formed from an ionic bond, we call it an ionic compound, or we say that it forms ions. Okay, so that takes care of the first part of the notes. We'll keep revisiting these concepts as we work through here, and we'll move on into the more notes later on this week. Thank you for listening.